Hello, and I'll do a few level 3 diode problems this time, because at level 3 we can no longer use those rules of thumb that we were using at level 1. They're just not going to be accurate enough. So I'll show you how you can get more accurate results, and it's a process of iteration. Normally we only have to do one iteration step to get close enough to the answer, and let's see how that goes. Right, here we've got actually, that's not a terribly interesting one, because the Zener diode here is never going to be in breakdown because its cathode here can never be more than 2.7 volts above the anode, and it's a 10 volt Zener, so that diode might as well not be in the circuit at all. It's just a potential divider equation. The answer would be 2.7 volts divided by 11k plus 16k. Let's try and find one in which the diode does actually make a difference. Much better. Okay, we've got 5.8 volts here, and that is flowing through a Zener diode here in the forward bias direction. In other words, it's going to behave just like an ordinary silicon diode. The reverse biased ordinary diode here we can neglect. It's only going to take about, in this case, 2 nanoamps through it, which is going to be negligible compared to the current flowing through this Zener diode here. So, first thing to do is to make our first guess of how much current is flowing. And our first guess can be made based on those rules of thumb we were using before. We could estimate that around about 0.6 volts is going to be dropped across that diode there, and therefore the current flowing would be about 5.2 volts divided by 1k, or approximately 5 milliamps or so. So we have 5 milliamps as our first estimate of the current that the ammeter is reading. But as I say, that may not be accurate enough. Let's make it more accurate by considering the Shockley diode equation as applied to that diode there. And it's a diode with a saturation current of 2 nanoamps and an ideality factor of 2. Right. If we've got 5 milliamps flowing through such a diode, then we could work out what the voltage across that diode is going to be much more accurately using the equation that the current through the diode is equal to the saturation current multiplied by e to the power of the voltage divided by 25 millivolts times the ideality factor minus 1. It's the Shockley diode equation. Here, that would be 5 milli divided by 2 nano, which would be, what, 2.5 times 10 to the power of 6, or 2.5 meg. If I bring the minus 1 over to this side, it will be 2.5 million plus 1. Almost not worth doing that. That's just going to be equal to 2.5 million for all practical purposes. So we can neglect the 1. Small compared to the 2.5 million. Take the natural log of both sides, and we would end up with log of 2.5 million equals V divided by, well, 25 milli times 2 is 50 milli, and that would give me a voltage of 50 millivolts times the natural log of 2.5 meg. And we can work that one out back on the calculator. 50 milli times the natural logarithm of 2.5 meg. Oops, 2.5 meg. And that is 0.736 approximately volts. So that would be a more accurate estimate of the voltage across this diode. Now, obviously, we've now got a more accurate estimate of the voltage across the diode. We could get a more accurate estimate of the current by doing 5.8 minus 0.73659 divided by 1k, and that would give me a current of 5.06341 milliamps. And I could take that current and go back through the equation again and work out an even more accurate value for the voltage dropped across this diode. But at level 3 and mostly at level 4, there's no need to go through the iteration process again. Just once is enough, and we could put in the answer as 5.06 milliamps. And yep, spot on. Let's see if we can find one where we use a Zener in reverse breakdown. Okay, this is a more interesting one, and it's a Zener diode in reverse breakdown, and it's clearly going to have some current flowing through it because we can quite easily get more than 3.3 volts across this Zener with a 7 volt source like this. At level 1 or level 2, we could probably just say that the Zener has a 3.3 volt breakdown voltage. It's in breakdown, therefore the voltage across it should be 3.3 volts. But this is level 3, and we need to be a bit more accurate than that. How do we be more accurate? Well, we have to take into account that the Zener diode has 3.3 volts across it when it's got 5 milliamps flowing through it. But here it doesn't have 5 milliamps flowing through it. We could estimate the current that it actually does have flowing through it by taking the 7 volts of the voltage source here, subtracting about 0.7 volts for this Zener diode, subtracting the approximately 3.3 volts that this diode will have, and that gives us 3 volts, which will drop across this resistor here. So the current through that resistor should be around about, well, that's 18.75 milliamps, which is quite a long way from 5 milliamps. So we've got 18.75 milliamps flowing through a Zener that is rated to have 3.3 volts across it at 5 milliamps of current and a dynamic resistance of 40 ohms. Okay, time to do some more detailed analysis. With a Zener diode, we can plot the current versus voltage characteristic, otherwise known as the IV characteristic. And in the forward direction here, it just looks like a normal silicon diode, so it will be an exponential curve, something like that. In the reverse direction, however, we know that it goes through a point which will be at 3.3 volts, or rather minus 3.3 volts, at minus 5 milliamps. That's what it's specified to do. A breakdown voltage of 3.3 volts at 5 milliamps of reverse current. So we know it goes through that point. We also know the gradient of this line. And we're assuming here a piecewise linear approximation to a Zener diode breakdown characteristic. It's just a straight line. And we know the gradient of that line is 1 over 40. It's the I versus V characteristic, and when you plot the current on the y-axis and the voltage on the x-axis, the gradient of any line is 1 over the resistance. So we know the gradient of this line, and we know one point on this line, so we can work out the equation of that line. No need to work out the equation actually, because all we want to know is where one particular point is. And that is the point when the current is minus 18.75 milliamps. What is this voltage here? I'll call it V. And it's greater than 3.3 volts by an amount which I'll call U. Well, consider this triangle here. The base of this triangle here is just U. The height of this triangle is the difference between minus 5 and minus 18.75 milliamps, so that's 13.75 milliamps. And we know that the gradient is the ratio of 13.75 milliamps to U. That's just gradient is height over width down here. So 1 over 40 is 13.75 milli divided by U. In other words, U is 40 times 13.75 milli. And that's the amount by which the breakdown voltage of this Zener diode in this circuit exceeds its rating of 3.3 volts. So we should be able to work out a better estimate now of what the actual breakdown voltage of this Zener is. And it's 3.3 plus 40 times 13.75 milli. Let's try that. Yeah, and that is close enough. It's not exact because the current through this Zener is not exactly 18.75 milliamps. We'd have to take into account the actual voltage across this Zener and the actual voltage across this ordinary silicon diode to work out the exact current through this resistor and therefore the exact voltage across this Zener, and that we'd have to do by iteration, just going through this process time and time again. But for level 3, going through it once is usually enough, and indeed that gets us close enough to the answer. That's it.